Hello everyone, I'm Sumant and I'm the mentor for the project titled Kinematic Analysis, Trajectory Planning and Workspace Representation for a 6 degree of freedom robot manipulator. Nishchay is the project junior and we have done this project under SAE NITK. In the current era, robotic arms are becoming more and more popular in modern industries. Today, every small and large industry uses the robotic manipulator to complete various tasks like picking and placing, welding process, painting, and material handling. Therefore, the research and simulation of robotic arms significantly improve the efficiency of using this tool in all sectors. The Unimation PUMA 560 robot arm was used as a basis because this is widely used in industry and academia. The 200 series was used for the first robotic brain biopsy in 1985. The 500 series is the most recognizable configuration, and the 700 series is the largest of the group and was intended for assembly line, paint, and welding work. The design was done using Fusion 360 software and it was imported into Simulink, and here the robotic arm was controlled by changing the values of the joint angles. Before we move to the kinematics part, I shall explain the DH model. The DH or the Denavit-Hartenberg kinematic model uses 4 parameters and is one of the most commonly used method for describing the robot kinematics. It uses 4 parameters like the link length, link offset, joint angle, and twist angle. A coordinate frame is attached to each joint and the DH parameters are determined. The DH parameters for the PUMA 560 robot arm has been listed in this table. Kinematics is the study of how things move, and here we don't look at what forces is causing that motion. Calculating the position and orientation of the end effector in terms of the joint variables is called forward kinematics. The general homogeneous matrix consists of the rotation and displacement vectors, and by multiplying all these transformation matrices, we can get the position of the end effector. The manual code for the forward kinematics was written using MATLAB, and the same results was verified using the existing inbuilt robotic toolbar functions fkind. In this figure, we can see that the position of the end effector is same in both cases. The exact opposite of the forward kinematics is the inverse kinematics. Here we convert the position and orientation of a manipulator end effector from Cartesian space to joint space. Tasks to be performed by a manipulator are in Cartesian space, whereas the actuators work in the joint space. Hence, we have to study the inverse kinematics of the robot arm. The main solution techniques for the inverse kinematic problems are the algebraic, geometric, and the numerical methods. And in this project, only the algebraic solution of the robot arm is examined. For a given position of end effector, all the possible joint angle solutions have been listed here. Next is the trajectory planning. The term trajectory refers to the displacement, velocity, and acceleration of the manipulator in motion. Task is to design the motion function of each joint of the arm based on certain tasks to be accomplished by its end actuators. Joint angle at the start point and at the end point is defined. The time is assumed to vary from 0 to 1 in intermediate steps. The joint velocity and accelerations is assumed to be 0 at the boundaries. By applying all these boundary conditions, we can find out the coefficients of the polynomial. It can be seen from the figures that the plots obtained are continuous and the movement is more smoother in the case of quintic polynomial interpolation. It indicates that this method is more feasible in the application of trajectory planning for similar 6 degree of freedom robotic arm. This method can make the robotic arm to run smoothly, reduce the occurrence of jitter and vibrations, and improve the stability of the system. The workspace refers to the set of all points that the robot arm can reach in space, and this can be used to determine the flexibility and accessibility of the robotic manipulator. The Monte Carlo method, also called the statistical simulation method, has been used to determine the workspace. Within the range of each joint variable, n random values from 0 to 1 are generated by the rand function, and in our case we have taken the sample points to be equal to 20,000. A large number of sample points also gives a more accurate workspace representation. The isometric view, top view, side view, and the sectional view of the workspace is represented here. From the figure, we can see that the workspace is an approximate ellipsoid and the simulated workspace range is accurate and closely matches with the actual workspace of the robotic arm. To summarize everything that we have done, the manual codes for the robot kinematics, trajectory planning, and the workspace were written in MATLAB, and the obtained results were verified using the inbuilt functions and the existing literature. The key takeaways by doing this project is that the members got a better understanding of the concept of robot kinematics. The limitations of our project is that the higher order polynomial interpolation for trajectories provide peaks of velocity in the middle, which is not desirable for multiple point trajectory. As part of the future work, trajectory planning can be done using optimization algorithms like PSO and GA, and fuzzy PID based dynamic control systems can be designed to have a more control over joint angles, velocity, and acceleration. The inverse kinematic equations could also be evaluated using the geometric approach or by making use of anthus. These are some of the important references used. Thank you.